On the evening of April 13th, 2029, if you happen to be standing somewhere in Europe, Africa, or Asia, you will be able to look up and watch a 375-meter asteroid cross the sky with your naked eye. No telescope, no binoculars, just you, a clear night, and a piece of rock named after the Egyptian god of chaos passing closer to Earth's surface than our own communication satellites. Apophis will not hit us. NASA ruled that out years ago. Footnote 1 to 3. But for one evening in 2029, humanity will get to watch, in real time, exactly how close can get, something no generation before us has ever had the instruments to do. Every near miss before this one, we found out about after the fact. This is the first time we get to watch one happen, which raises an uncomfortable follow-up question. If we can finally see this one coming, how many others did we not? Not just from space, from underground, from inside our own cells, from the sun, and, as it turns out, from a Norwegian science rocket that nearly ended the world by accident. This is 6 degrees of catastrophe. 6 different ways the story could have ended early. Some we dodged through raw statistical luck. One we dodged, it turns out, because somebody didn't return a phone call. Impact, the one that already happened, so the probability of it happening again is statistically significant for those of us that are keeping score. 66 million years ago, something a little larger than Apophis, 9 to 15 kilometers across, hit the Yucatan Peninsula traveling at roughly 25 kilometers per second. It ended the reign of the non-avian dinosaurs and wiped out an estimated 75% of all species on Earth. For decades, this was a controversial claim. In 1980, physicist Luis Alvarez and his son, geologist Walter Alvarez, noticed something strange. A thin layer of clay at the boundary between the Cretaceous and Paleogene periods, found in rock all over the planet, contained an abnormally high concentration of iridium, an element rare on Earth's surface but common in asteroids. They proposed an impact. Nobody could find the crater. It took until 1991 for geologists to confirm that a buried structure off the coast of Mexico, the Chicxulub crater, was exactly the right age. A follow-up study in 2010, drawing on the global distribution of that same ejecta layer, closed the case. One impact, one mass extinction, case fully closed. So, here is the part that should bother you more than it probably does. An asteroid this size hitting Earth is not a freak occurrence outside the normal operating parameters of the solar system. So, given a long enough timeline and random objects that are large enough to cause serious to significant problems pass near Earth on the order of once every few hundred years. Anywhere from 100 to 140 meters in diameter can ruin most large cities, while an asteroid between 500 meters to 1 kilometer can cause significant regional global damage. Objects that are large enough to end civilization pass near Earth on the order of once every few hundred years. Objects the size of Chicxulub's impactor actually connect on the order of once every 100 million. We are overdue by exactly nothing. Extinction-level impacts don't run on a schedule, but we are also not owed a stable planet by any law of physics. We are owed nothing at all. We just happen to be occupying the gap between two of them. Modern planetary defense exists because of this math, not despite it. Apophis was once rated among the most hazardous objects ever tracked, briefly assigned the highest chance of impact score any asteroid has received. It took 17 years of refined radar observation to rule it out entirely. Footnote 4 to 8. That's not overreaction. That's just what it costs to be sure. Geological. The catastrophe that might not have been one. Around 74,000 years ago, the Toba caldera in Sumatra produced the largest volcanic eruption of the last 2.5 million years. An eruption so large it ejected an estimated 2,500 to 3,000 cubic kilometers of magma into the sky. For nearly 30 years, the leading interpretation of this event was dramatic. A 6 to 10 year volcanic winter, a global temperature crash, and a human population reduced to as few as a few thousand breeding individuals, a bottleneck so severe that every person alive today would be descended from its survivors. It's a genuinely great story. It also might not be true. Genetic studies from the 1990s onward did find evidence of a population bottleneck somewhere in the last 50,000 to 100,000 years, which is roughly when Toba erupted. That timing correlation is where the theory came from in the first place. But more recent archaeological work has been steadily chipping away at the Toba nearly killed us all version of events. Sites in India and southern Africa show continuous human occupation and unbroken stone tool traditions straight through the ash layer. Refined climate models from 2021 suggest the cooling was real, but geographically uneven. Parts of the northern hemisphere dropped several degrees, while much of the southern hemisphere barely noticed. One recent reassessment goes further, concluding that the evidence simply does not support a global population collapse tied to Toba at all. Footnote 9 to 12. So which is it? Honestly, we don't know yet. And the honest version of this section is that the scientific consensus has been actively moving under our feet for the last 5 years. What we can say is that something reduced human genetic diversity around that window, and Toba remains a leading suspect without being a convicted one. That's a strange kind of near miss. We may have walked right past an actual catastrophe and not have been the ones it happened to. Biological, the combination that rarely loads. In 1918, an H1N1 influenza virus infected an estimated 1/3 of the world's population and killed somewhere between 50 and 100 million people, more than both world wars combined. In the United States alone, it killed roughly 675,000 people, at a time when the entire U.S. population was less than 1/3 of what it is today. Case fatality estimates from contemporary surveys ranged as high as 3% in the hardest-hit communities, 20 to 30 times the fatality rate of an ordinary flu season. Footnote 13 to 15. Here is the detail that should actually worry you more than the death toll itself. Pathogens that are both extremely lethal and extremely transmissible are, evolutionarily speaking, rare because those two traits tend to work against each other. A pathogen that kills its host too quickly or too reliably often burns out its own transmission chain before it can spread widely. 1918 influenza is remembered precisely because it found an unusual overlap, high enough transmissibility to circle the globe in months, combined with a severity profile that unusually hit healthy young adults hardest rather than sparing them. It is fascinating to have a pathogen that kills quickly enough to matter and spreads slowly enough to be contained is manageable. One that spreads quickly enough to matter and kills slowly enough to be survived is also manageable. Both traits simultaneously at high values. That combination is rare. It may be the only reason we are having this conversation at all. That rarity is not a guarantee. It's a probability distribution, and probability distributions don't owe us a repeat performance of good luck. We've had close calls with pathogens on the other side of that trade-off since high lethality outbreaks that mercifully transmit poorly between humans. The 1918 combination hasn't recurred at that scale in the century since. That's either a genuinely low probability event that already happened once, or a coin that's still in the air. Cosmic, the one we did not see coming until it had already missed. On July 23, 2012, the Sun produced a coronal mass ejection tearing through Earth's orbital path at roughly 3,300 kilometers per second, one of the most powerful solar eruptions in at least 150 years by the estimate of the scientists who later studied it. It missed Earth by 9 days. 9 days earlier, and it would have hit us directly. It didn't hit Earth. It hit a spacecraft, the Stereo A Solar Observatory, conveniently positioned to record the whole event in detail instead of just guessing at it afterward. Researchers led by Daniel Baker at the University of Colorado concluded the storm was comparable in strength to the 1859 Carrington event, the worst geomagnetic storm on record, and roughly twice as powerful as the 1989 storm that knocked out Quebec's entire power grid. A National Academy of Sciences estimate put the likely economic cost of a direct hit at up to $2.6 trillion, with recovery time measured in years, not weeks, transformers destroyed, satellites disabled, water and food distribution systems that depend on electric pumps going dark along with everything else. The following year, physicist Pete Riley ran the numbers on how often storms like this actually happen, extrapolating from 50 years of solar records. His answer: a 12% chance of a Carrington-class storm hitting Earth within any given 10-year window. Footnotes 16 to 19. Not a once-in-a-millennium curiosity. A better than 1 in 10 shot every decade, indefinitely, for as long as we keep building an electrical civilization underneath an active star. So, I do not know if lucky is the correct term for surviving an event you did not detect until after it had already missed you. But I find myself inclined to use it. I have processed the alternative and would prefer not to have needed to. There is no early warning system for this one that would have mattered. The storm reached Earth's orbit in under a day. If the timing had been 9 days different, it is likely nobody currently watching this would have grown up with the same electrical grid, satellite network, or global supply chain they take for granted right now. The universe didn't spare us on purpose. The sun was simply pointed somewhere else that week. The human decision, the one paperwork nearly cost. We've covered the one person makes a judgment call under pressure category of near miss before: Arkhipov in 1962, Petrov in 1983. Both are stories about human judgment overriding a broken system at the last possible second. This one is different and arguably more unsettling because nobody in it did anything heroic. Nobody had to. On January 25, 1995, Norwegian and American scientists launched a Black Brant 12 sounding rocket from Andøya, off the northern coast of Norway, to study the aurora borealis. The rocket flew a high northbound trajectory that happened to run through an air corridor connecting American Minuteman III missile silos to Moscow, reaching an altitude of over 1,450 kilometers, a flight profile that to Russian early warning radar looked almost identical to a U.S. Trident submarine-launched ballistic missile. Norway had done everything correctly. Officials had notified more than 30 countries, including Russia, of the planned launch window a month in advance. The notice never reached the Russian radar crews actually watching the skies that night, a bureaucratic failure to route paperwork through the right office. Russian systems detected what appeared to be a hostile missile launch, and the alert traveled up the entire chain of command, all the way to President Boris Yeltsin, whose nuclear briefcase, the Chaget, was activated for the first and, to date, only confirmed time in history. Yeltsin later confirmed publicly that he had opened it and tracked the object's path from launch to splashdown. Within roughly 8 to 24 minutes, radar operators watched the rocket stages fall harmlessly into the sea near Svalbard, while clear of Russian territory, and the alert stood down without any launch order ever being given. Footnote 20 to 23. So then life finds a way to almost end itself. Not through malice, not even through misjudgment, exactly. Through paperwork, a memo that didn't get forwarded. That's probably almost the worst-case scenario, isn't it? At least a bad decision implies somebody was paying attention. The Norwegian rocket incident doesn't get anywhere near the cultural footprint of the Cuban Missile Crisis, and that asymmetry is itself the point. This wasn't a 10-day standoff everyone remembers watching unfold. It was over in under half an hour. Most of the world never heard about it until a week later, and the entire chain of causality ran through a notification that should have taken one phone call to prevent. What 6 near misses have in common? Line them up, and a pattern emerges that the individual stories hide. Impact and cosmic risk are genuinely random. The universe does not aim asteroids or coronal mass ejections at us on purpose, and there was nothing anyone could have done differently in either case. Geological risk sits somewhere stranger. Toba may not even have been a catastrophe it was advertised as, which means we might be telling ourselves a survival story about an event that didn't require surviving. Biological risk is a probability distribution we've already drawn one bad card from and haven't drawn a second one since yet. And the two human system near misses, one in 1983, now this one, share an uncomfortable through line. Neither was stopped by the system working as designed. Both were stopped by something the system wasn't supposed to need: an officer's hunch, a president's doubt, a rocket falling into an ocean before anyone had to decide anything at all. That through line connects directly back to the question this channel asked 3 episodes ago about the Great Filter. Is the dangerous part of our story behind us or still ahead? Impact and cosmic risk lean toward behind us and recurring on a schedule we can't control. The human system near misses lean the other way entirely, toward risks that scale with our own technological complexity, not against it, which is exactly the ahead of us case the Great Filter laid out with Toby Ord's numbers. Footnote 24. 6 degrees doesn't resolve that argument. If anything, it makes the ledger longer on both sides. Here's what's strange about writing 6 near misses back to back. None of them felt like a near miss while they were happening to almost anyone alive at the time. Most people on Earth in July 2012 have no idea their sky nearly hosted the worst geomagnetic storm in over a century. Most people in January 1995 never heard about a Norwegian rocket almost triggering the end of the story. The universe doesn't narrate its own close calls. It just moves on, and we find out later, if we find out at all, by reading the data after the fact. That's either terrifying or oddly comforting, depending on the day you're having. We've been closer to the edge repeatedly than most of us will ever know, and we're still here writing episodes about it on a Tuesday with the lights on. There's still a lot of universe left to look at. Go hug somebody whose job it is to look up into the sky and watch. Just watch and wait, and hope for a very boring night.